Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to third week of the session. This is first lecture of third week for wireless and mobile communication. If you recall, in our last lecture, we talked about the effect of clustering on the overall capacity of the system, and we discussed that through clustering we can reuse the frequencies in a certain coverage region. Eventually that leads to overall increase in the capacity of the system. So the clustering is one of the important principles through which we can increase the capacity of the system, even if we had a limited spectrum for use of subscribers. And if you recall, we discussed that there was an important parameter regarding clustering, which was the cluster size. If we have smaller cluster size, that means we would be needing more clusters to cover a specific region, and that leads to more reuse of the frequency and more capacity. That means in order to increase the capacity of the network, we generally go for reducing the cluster size. So one of the important parameter was cluster size, through which we can change the capacity of the system. In today's lecture, we are going to talk about another important parameter, which is interference. And as we discussed in our last week's discussion, interference actually limits the capacity of the system. So in today's lecture, we want to discuss how does this interference limits the capacity, or in other words, what is the relationship between interference and the system capacity. In order to understand the relationship between interference and system capacity, we must understand the relationship between interference and the cluster size. If you recall, in our last lecture, we have already established a relationship between cluster size and system capacity. And in today's lecture, of course, as I said, we want to establish a relationship between interference and the cluster size. And eventually we would end up with defining how interference would limit the system capacity by limiting the value of cluster size. So let us start today's discussion. So as I said, the interference is actually one of the major limiting factor on the performance of the cellular radio system, because the interference is actually degrading the overall communication. If in any system, if any communication is affected by another interference, that means that interference would cause errors in that communication, or eventually if you want to have a reasonable quality of service in any system, that means we have to limit the interference up to a certain value. So there is a maximum tolerable limit for each system, beyond which we cannot allow the interference. So generally, whenever we are deciding or designing a system, we try to establish things in such a way that the overall interference limits below that tolerable limit. Generally in cellular systems or wireless systems, this interference is actually a bottleneck in increasing the capacity, because as we intend to increase the capacity, that leads to more interference, and if we try to reduce interference, that leads to a decreased capacity. So basically there is a trade-off between interference and capacity. So we have to decide we have to design the system in such a way that the interference remains to a tolerable limit, as well as we can get the maximum capacity out of the system. So the question is, how does this interference occur in a cellular system? So there are many sources of interference. If you think of mobile in the same cell that is being used, so it may cause an interference. there is a possibility that a call in a neighboring cell also causes interference to a certain user. Similarly, the base station which is operated at at the same frequency would also cause the interference, as we discussed in our last lecture as well, that there is a co-channel which uses the same frequency, and of course those co-channel also causes the interference. It may be possible that there may be some other systems which are non-cellular and they may be operating in a frequency which causes interference to a mobile user. So potentially there are variety of different sources that can cause interference in a communication system. Of course, from system point of view, we would be limiting our discussion to the interference which occur from the system, the cellular system. So basically these interference types, they can be classified into two major categories of interference. First one is known as co-channel interference. What is co-channel? We have discussed in our last lecture that co-channel is the channel which uses the same frequency which as the channel as a cell under study. So these co-channels, they are also leaking energy in the intended frequency band. So therefore the interference which is coming from the co-channel is actually named as the co-channel interference. Second type of interference is named as adjacent channel interference. Adjacent channel interference is coming from other channels which are used in the same cell, as we discussed in our last lecture as well. When we make a frequency reuse plan, certain frequencies or certain channels are allocated to each cell. So for example, a cell has four channels. So if one channel is being used, the second channel can potentially cause interference to the first channel, although the frequency of second channel may be slightly different, but due to improper filtering or other limiting factors or non-ideality of circuit, there is some residual energy in the frequency bands which cannot be eliminated. In that case, that energy causes an interference to the adjacent channels. So basically our subsequent discussion will be focusing on these two types of interferences, which is first one is the co-channel interference and second is the adjacent channel interference. One thing to point out at this stage is that we can expect interference at both voice channel as well as control channel. So interference is not limited to the voice channel. Basically it can occur at control channel as well. If we are having interferences in voice channel, in that case the subscriber will be hearing a crosstalk, or it will be getting signals from some other user, so which is generally named as crosstalk. So in that case a user would be hearing some unwanted distortion, some unwanted signals at the background coming from this crosstalk. Similarly, if the interference occurs at a control channel, because control channel are primarily used for digital signaling, so this interference can potentially cause error in the digital signaling, and those errors in the digital signaling would lead to missed calls or blocked calls because of that interference. So of course we don't want interference at the voice channel as well as the control channel. So let us move our discussion to the two types of interferences. Let me start with the basic parameter which we use to categorize interference, because the interference in absolute terms has no meaning. Generally interference is evaluated on the basis of the signal strength. So uh, if a strong signal gets a strong interference, it may be equivalent to a weak signal getting a weaker interference. So the term interference is actually studied in comparison to the actual desired signal. Therefore, in systems, the parameter that we use to characterize interference in the system is actually the signal to interference ratio. This signal to interference ratio is one of the important parameter. And how do we define this signal to interference ratio? SIR is actually the ratio of received signal power to the received interference power. And as I said, there can be variety of different sources of interference, so we have to account for all those interference or interfering sources and include all those powers. So basically, this signal to interference ratio is actually the ratio of received signal power to the received interference power. At this stage, I would like to make some comments about other types of systems as well. In your previous course of communication systems, you may have talked about another parameter, which is signal to noise ratio. If you recall, typically in wired communication system or the guided media communication system, the effect of noise is more prominent as compared to interference, because the signal is confined to a specific region in a guided media communication. In that case, if a system is properly designed, the interference can easily be limited to a specific value. In that case, the most important parameter becomes noise, not the interference, and therefore we use a signal to noise ratio as a performance metric in all those systems. But in wireless communication system, because the signal has to go through free space and the signal can interfere with any other potential user, in that case interference is generally dominant as compared to noise, although there is noise as well. But in comparison to interference, in most cases the noise becomes insignificant as compared to the interference. So generally the wireless communication systems, they are considered as interference limited signals rather than noise limited. Therefore we use a performance metric of signal to interference ratio, and we generally do not use signal to noise ratio. However, there are possibilities of having system in which noise and interference both have significant effect, and we cannot neglect any of those. So in such systems, the performance metric that we should use is signal to interference plus noise ratio. In that case, we have to include interference power as well as the noise power as well. And the definition in all cases remains the same. The signal to noise ratio is actually signal power to the noise power. It's a ratio. Signal to interference ratio is also a ratio. Signal power to the interference power. And signal to noise plus interference plus noise ratio is also a ratio, but in that case we take ratio between signal power divided by the interference power plus noise power. So both of them, they are in the denominator, leading to this interference value. So the parameter, what I want to say is that the specific parameter that we use for analysis of system is dependent on the type of the system. So from our point of view, we will be using this signal to interference ratio because the interference is treated as the dominant effect in the wireless communication systems. So let us now move to our first type of interference first type of interference that occurs in the cellular system, which is co-channel interference. So what is co-channel interference? Co-channel interference is the interference which is coming from the co-channels. Unlike the signal to noise ratio, if you recall, you must have talked in the previous course of communication system, if we want to reduce the effect of signal to noise ratio, a simple procedure is to increase the signal power. If you increase the signal power, eventually the ratio, signal to noise ratio increases, so eventually the effect of noise decreases. So but this procedure is not applicable to the case of interference. Why is not possible? Because if you increase the carrier power, that means you have to increase the carrier power in the co-channels as well, and if you increase the carrier power in co-channels, eventually there will be more power in the interference. So if you increase transmit carrier power, in that case interference power also increases, and the signal to interference ratio, it remains same. So basically this co-channel interference, it does not change with increasing the signal power. In most cases you can conveniently take it as independent of the transmission power. So the carrier transmit power changing procedure that we use to reduce the effect of noise is not applicable to the reducing the interference power. So how should we decrease this effect of interference? In order to decrease the effect of interference, or in order to increase the signal to interference ratio, we have to reduce the power which is coming from a distant co-channel, and this can be done only if we physically separate a co-channel from the actual base station, the serving base station. So in order to reduce co-channel interference, we try to move co-channel from the serving base station as far as possible. So if they are physically separated, eventually the signal has to travel longer distances to reach the serving base station, and that leads to the lower co-channel interference. So the only procedure to reduce the co-channel interference is to increase the separation between two co-channels. So if we want to mathematically represent this effect of co-channel interference, how can we do that? So let us assume that the radius of cell is represented by R, and the nearest co-channel, the distance between nearest co-channel is separated by D. If we want to separate the co-channels, it means physically place physically farther distances, in that case we want to increase this value of D, or in other words we want to increase the value of this ratio D by R. So physical separation means we want to increase this ratio D over R so that we get smaller value of interference, because if we increase the D by R value, it gives more isolation in the radio frequency, leading to reduced interference. In some cases we use another parameter to represent this ratio D by R. This ratio D by R is represented as co-channel reuse ratio, or in our textbook this parameter is represented by parameter Q. So in order to physically separate the co-channels, we want to increase this Q. Actually this Q gives an indication of how often frequencies are being reused. And let us discuss a simple scenario. These are some this table. If you look at this table, actually it relates a cluster size to the co-channel reuse ratio. If you have a cluster size of 3, that means co-channel reuse ratio is also 3. But if you have a cluster size of 7, in that case this reuse ratio becomes 4.58. For cluster size of 12, we have reuse ratio of 6, and so on. You can see these are the commonly used values of I and J that we use in typical systems. Mathematically this co-channel reuse ratio is related to the cluster size with this relationship which is under root 3 into n. but you must note that this relationship was derived on the basis of hexagonal geometry. So for the case of hexagonal geometry, which we are considering in our studies, this co-channel reuse ratio is actually represented by under root 3n. And you can see that if we have a small value of q, and that means the cluster size n is also small. And having cluster size small means you would be needing more clusters to cover the region, and more cluster means there will be more use of frequencies, and if this more use of frequency, that means there is more capacity. So the smaller value of q is actually related to a larger capacity, but because we have reduced the cluster size, in that case the co-channels will be close to each other, and in that case the interference will be high. So a small q value relates to a small q value represents that there is a increased interference between co-channels, but the overall capacity increased. On the contrary, if we use a larger value of q, larger value of q means there will be a larger value of cluster size, and having larger value of cluster size means we are placing co-channels at the farther distance, so eventually that will give lesser interference. So a larger value of q improves the transmission quality because the co-channel interference is reduced. So the smaller level of co-channel interference is obtained when we keep a large value of q, but eventually if we go for a large value of q, that means we are going for a large value of cluster size, and if we are going for a large value of cluster size, that means the overall capacity is reduced. So you see that if we intend to increase the capacity, we have to use a smaller value of q that leads to higher interference, and if we want to reduce the interference, we have to go for a larger value of q and reducing the capacity. That means again there is a trade-off between two objectives of cellular system design, because we intend to reduce the cluster, at same time we want to increase the capacity. So increasing capacity and reducing interference, they are contradictory objectives, and when we are designing a system, we have to make a trade-off to get the maximum possible benefit of these two. So let us proceed mathematically in this regard, assuming that we have the signal which is represented, whose received power is represented by a symbol S, and there are number of interference which are producing co-channel interference, and we are representing them. The interference power is represented by I with subscript of small I, and the total number of interference, they are represented by I0. So there are number of I0 number of interfering co-channels which are causing some interference to a signal which is represented by whose power is represented by S. Therefore the signal to interference ratio, as we defined, that is the ratio of signal power to the interference power. It can be represented as S, which is signal power, divided by, we have to include all the powers coming from all the interferences, so I1 plus I2 plus I3 up to I0. So these are all the interfering powers. So this signal to interference ratio in this particular case can be represented by S divided by summation of powers of all the interfering signals. And of course, if we can calculate the power which is coming from all the co-channels, then this signal to interference ratio at any subscriber mobile station, we can calculate that signal to interference ratio. Generally, you must note that the interference signal to interference ratio for the co-channel cell is important parameter for the forward link, because this is generally calculated at the mobile station. So for any mobile user, this forward link signal to interference ratio can be calculated if we can calculate the power of the signal coming from the serving base station, and we can calculate the power of signals which are coming from the interfering base stations. The question is how we can calculate the power, because each co-channel is placed at a certain distance. So is there any relationship between the power and the distance between the mobile and the base station? So the answer is lies in the radiation pattern. This is a simple scenario of received power in a wireless communication system. Because assume that the base station is placed at the center. We have an omnidirectional antenna. It radiates power in all directions. As the power goes in all directions, the power density is actually the same, and as we move away from the base station, the total received power gets reduced. So if you are at this first circle means if a mobile user is very close to the base station, it will be receiving very high power. And if it moves backward, that means away from the base station, and if in the second circle region, still it will be receiving a high amount of power from the base station. As it moves away from the base station, the power gets reduced. In the third circle, there will be received power, but that will be a medium power as compared to what you receive in the first circle. Similarly, as the mobile station moves backward, that means away from the base station, the power gets further reduced. So you will be receiving even lower power, and at the outer circle, the mobile station will be receiving very low power. As long as the power level is above the minimum detectable level or minimum threshold to maintain the call with the base station, the mobile station can communicate with the base station. As soon as the power level goes below the acceptable minimum value to maintain the call, in that case the call gets dropped. And if the mobile station goes beyond this region, so there will be very extremely low amount of power received at the base station, and eventually this base station will not be able to provide coverage in this region which is outside this shaded part. So the thing that I want to explain is that as we increase the distance from the base station, the overall power which is received at the mobile station gets reduced. So how can we mathematically represent this power? So our propagation measurement of different mobile cellular systems, they indicate that the received power or received signal strength, it decays as a power law, means it decays as a power of a distance separation between transmitter and receiver. So if in certain environment there is a square law power reduction, in that case if we increase the distance, the power will be increased by distance squared. Or if there is a third law, that means the power will decrease with distance cube, and so on. So generally the propagation measurement show that this received power is dependent on the some power of the distance. This power which I have represented here as n, this n is known as path loss exponent, because it shows that how the power is reducing as we are increasing the distance. In some text, this path loss exponent is written as path loss index. So they are two equivalent terms. So path loss exponent and path loss index, they are one of the important parameters which actually depend on the propagation environment. For different types of environments, the path loss index is different. For example, if you are in an open environment, free space, where there is no buildings or any obstruction, in that case this path loss exponent generally has a value of 2. But if you are in a densely populated environment, for example an urban area like Karachi, where you have lots of obstruction and buildings and different types of vehicle, in that case we have a relatively higher path loss exponent, and typically that goes close to 4. So in most cases this path loss exponent range from 2 to 4 for different environments. So how do we represent PR, this received power at resistance? The mathematical procedure is that we define certain point. For example, a point close to this base station, we take this point as a reference point, represent its distance as d naught, and whatever power is there we represent it as p naught. So P naught actually represent a power which we have taken as the reference at a reference distance d naught. In that case, if you want to calculate power at a specific distance from the base station, that power is represented by PR is equal to P naught into d upon d naught raised to power minus n. So you can see that this received power is dependent on the distance or separation between the base station and the mobile station, as well as this path loss index n, which is dependent on the propagation environment. So through this formula we can calculate the received power, and this formula is acceptable to all types of base stations, not necessarily for serving base station. So we can use the same formula to calculate received power from the serving base station as well as from the interfering co-channels. So let us go back to this slide. So as we said, we want to calculate signal to interference ratio for different interference. So this signal to interference ratio, it should be represented as S divided by the sum of power received through all the interferences. So this is the formula. So co-channel interference is signal power divided by all I's. How can we calculate signal power? We have defined the relationship between signal power and the reference power, which is given by this formula. So this signal power coming from the serving base station S, it can be represented as P naught multiplied by this D naught is the same, and D should be distance of mobile from the serving tower, and of course this raised to power minus n is same as we used in the formula. Similarly, the interference power, in that case this reference distance and the reference power, it remains the same. So P naught divided by D naught, these are the same, but the distances, they should be calculated from each of the ith interferer. So you have to calculate the distance from the mobile station to first co-channel interference, and then similarly we have to calculate the signal power at the distance between the mobile station to the second co-channel interferer and mobile station and third co-channel interferer, and so on. And you can see that as we have we generally use a fixed reference distance at all base stations. So this D naught factor, and this p naught factor it becomes common in numerator and denominator, so they will cancel out eventually. P naught with this denominator p naught, and d naught raised to r minus n with this denominator d naught raised to r minus n, they will go away. So we can write signal to interference ratio as distance of mobile from serving tower raised to r minus n, and the distance from ith interference which is raised to power minus n. So basically you can see that this signal to interference ratio is actually dependent on the distance of co-channel cell. If we change the distance, as we discussed in the initial slides, we can change the signal to interference ratio. This is the generalized formula which we can use in any circumstances, but to make a reasonable or comprehensible results out of this formula, let us make some assumptions. Of course there will be some approximation, but those are not major approximations, and they can give reasonably very good result for our understanding. So first thing that I want to show is that because we are reusing frequency again and again, so there are different types of interferers which are present in that particular system. We are focusing on co-channel interference, so let us see how many co-channel interferers will be there in a certain system. For example, let us see this red cell. It shows a specific serving base station. So this is the actual cell which is our under consideration for this our analysis. Of course, if we are using a reuse pattern, so these frequencies will be reused. So if we have a cluster size of n is equal to 7, in that case this cluster will be 7 and this frequency will be reused at some other cluster like shown here with green colors. So the same frequency is there, and similarly because this pattern is being replicated, you can see this frequency will appear in another cluster which is at relatively farther distance, which is shown by this dark blue cell. This one has also the same frequency, or these are the co-channel. So basically the co-channel interference will come from these green cells as well as from these blue cells, and if the this clustering is replicated out in farther distances, so again there will be interferer at relatively farther distances which will be causing interference, co-channel interference. So in our terminology, because this green they are closest in distance, they are generally called first tier interferer or first tier co-channel cells. These blue, they are actually second tier co-channel cells. Similarly, if we replicate this outward, there will be a third tier of co-channel cells and fourth tier of co-channel cells and so on. So the important thing that I want to show here is that there are number of co-channel interferers which are present, but those interferers are not at the same distance from the serving station. You can see this first tier interferer, they are closer to this serving base station, but the second tier interferer, they are at relatively larger distance. Similarly, the third tier will be farther away, and fourth tier and higher order co-channel cells, they will be at relatively farther distances. As we discussed that increasing the distance reduces the amount of received power and amount of interference which is coming. So we can conveniently assume that the dominant interference will be coming from these first tier interferers. The second tier and all other higher order tiers, they will cause interference, but in comparison to the first tier interference, we can neglect all those. So first assumption that we want to make is that the first air interferer, they are actually the dominant interference, which cause the dominant interference, and we would reduce the co-channel interference which is coming from the higher order tiers. So this is one thing. So again, let us go back to this co-channel interference stuff. So signal to interference ratio, we have to use this formula, and because we are limiting our discussion to only first tier interferers, so we will be taking the distances from the rth tier interference. So this is our first assumption, that we will be taking only first tier interferer for the calculation of co-channel interference. We will continue this discussion in our second lecture. From this point, I want to stop here, as the time we have already passed beyond our time. So let us stop the lecture here. We will continue our discussion from this point onwards. Thank you all.